meetup of KW Intersections. Just quickly wondering, whose is its first time today? Hoping you enjoy it and come next time. So the first speaker of today will be Michal Kononenko, and he will be talking about quantum machine learning. So he did an internship at the Institute for Quantum Computing, and he is currently back in school again, and he is studying nanotechnology. So, give him all.
So before I start, how many of you guys have experience in quantum computing or read about it somewhere tonight? Okay, goodbye. So as Mary said, I'm a third-year nanotech engineering student at the University of Waterloo. About a month ago, I finished up an 8-month internship at the Institute for Quantum Computing. And since I've been at this meetup for about 6 months, not really contributing, I figured this would be a good time to make my first contribution. So this is probably, I'm not sure how representative this talk will be of the other talks we have here. I think Mary will attest to that a bit more. But without further ado, let's start. So quantum machine learning, or how I learned to stop worrying and love the Hamiltonian. So, okay, we skip this part. So this talk is based on a paper from 2014 by Schuld. There's a link to it on the meetup page. And basically the problem that we're trying to solve is the clustering problem. I'm learning along with you guys, so if I can help with anything. This is my first talk here, so if anybody's got anything they want to ask. Yep.
How long did it take to get comfortable with the first parts of?
So here's the timeline of the project. 4 weeks ago is about when I agreed to do about 4 weeks ago. So 3 weeks ago my work term was wrapping up, and I was working on a report. I was working on a big report to do that. 2 weeks ago, 3 weeks ago I procrastinated. So I just did like a bit of research for this, just trying to figure out how somehow I could tie in the work you guys do with computer science into what I did with quantum computing, with what I did with my cursory understanding of quantum computing, which is probably a bit wrong, but to my cursory understanding of quantum computing. That was 3 weeks ago. 2 weeks ago I had major reports. 2 weeks ago I had that report that I was working on that was due. 1 week ago I had like 4 assignments due, and this week is midterms. So I literally coded this up 3 hours ago, like 2 hours ago as I was working. As I got it on my midterm. Yes?
I was lost quite a while ago, but just trying to get my handle on how this fits the K-means clustering problem. What exactly do you have in superposition? So you're basically saying the CK is, you don't know what that is, so you want that to be a superposition of all possible values. And you're doing for each sample in the data set, comparing it to that quantum superposition for CK to get the closest one?
What you're actually doing is you're having your X is actually out. So what I did was I've abstracted out here. So X is actually a superposition of all your possible. Your X is superposition is your entire feature vector now. So it's going to be some alpha 0, 0, 0, plus beta 0, 0, 0, 1 plus
for one sample or for the whole samples?
Just for one feature. So one feature vector. Because quantum mechanics, the thing with quantum mechanics is it's dealing with state vectors in a Hilbert space, and a lot of the problems that we have in machine learning deal with large dimensional vectors in a Hilbert space. So
if you were to sort of flip the problem around, you might be able to use that QRAM to deal with different
principal component analysis using this method. So PCA, I think, Mary, did you choose that topic because you knew what I was going to talk about, or was it just coincidence that that topic came out? The power method.
I just got the feeling I want to show this.
Because principal component analysis involves finding the eigenvalues and eigenvectors of a humongous vector space. And working with quantum systems, you also end up finding eigenvalues and eigenvectors in the complex vector space. Then gives you things like the energy and gives things like the position and momentum. So putting that to a quantum computer, you can't speed up PCA. You can speed up algorithms like PCA like this as well, but it wouldn't be with a swap test. It would be a different quantum circuit that you would run.
wanted to clarify something. Did you say if I apply the Hadamard gate twice, it acts like a NOT gate?
Yes.
That doesn't match my calculations. Because the Hadamard gate is like 1, 1, 1 minus 1, and that's got a factor of 1 or root 2 on it. If I multiply it twice, I don't really get a NOT gate. Right? Because the NOT gate's like 0, 1, 0.
When you square that, 1, 1, 1 minus 1.
Like,
So
that
then
gives
you
you, that gives you the identity.
that gives you the
Okay.
identity. No, it's not.
The cake it is itself transposed adjoint, so
Yeah.
it is its inverse.
It's in yeah.
It is a self-inverse. So
Right. So it's gonna be the matrix. So it's got a point. It should be actually the sigma x. So was the actually I'm thinking that's
Could be similar.
it could be sim. Sorry.
Yeah, it could be the same.
It could be the same idea, but like if you pass in a superposition, yeah, sorry, if you pass in, it's really, so it's not really the square root. So square root of naught, sorry, that would have to be like a different, that would be like a pi over 2 phase gauge. So yeah, again, I was wrong. See, I was wrong about the Hadamard being this, I was wrong about the Hadamard being the square root of naught. It's just, the principal value of the Hadamard is that it forces it into a superposition. So yeah, I'm sorry I made a mistake. With that, that should be there is a phase gauge that if you apply twice using I think it's the pi over 2. It will be the pi over 2 phase gauge. So what I was trying to say is that you can apply a pi over 2. If you look at the block, if you go with the block sphere, you can apply a pi over 2 rotation, which is actually it should be, I think it's sigma x, which is the square root of naught, which is sigma x the square root of naught.
you get a square root of naught if the minus sign is off diagonal.
Yeah.
I think.
Right. So yeah, sigma.
Not for x, but for Hadamard gate.
Yeah.
If you put the minus sign not on a diagonal,
But on the off diagonal.
but off diagonal, I think that should work. But
Yeah. So, but yeah, and then it's possible. Again, it's possible to do it. It's possible to do it. Maybe if you put it on the off diagonal, but even then, it's like I think it would work if you put it. I think it would work if you put it off diagonal. I have to go to the math myself and figure it out, but. Yeah, there are gates you can design that you can apply twice and get a knot. So and you can't do that on a classical computer. In a Boolean algebra.
Are you familiar with the work at the Institute of Quantum Computing here in Waterloo regarding a programming language for quantum machines?
So in terms of programming for quantum machines, I haven't been. I know a couple of friends who are doing work in. They're looking more into quantum circuit synthesis. So what IBM's just released with their quantum computer, they're looking for methods to sort of automate that. In terms of programming languages proper that are available for quantum machines, I will take a look at QML. It's called. I've read a thesis about that at one point. That's trying to be like a formal machine. That's trying to be like a formal simulator language for quantum machines written in C++. And recently there was one LangQ, which is trying to be an imperative language for quantum machines, and that one runs on top. That one runs on the JVM. So if you want to run your simulations on that, that might be that might also be a good place to start if you don't want to work with IBM's GUI.
to ask a quick question. So those vectors CK, they represent the centers of the clusters, right?
Yes, so there's state that you get from there's state that you prepare from
I mean, for them to be quantum states, they need to have norm 1, right? The Euclidean norm.
They do have to, yes, they have, the state's going to have the state's going to have
Does that, because not all vectors you might care about have maybe I'm missing something. Does that play? Because all those x vectors and all those CK vectors, you cannot put any vector there because then the expression doesn't make sense anymore.
Yeah, the Schultz paper goes into detail about how that state's actually prepared. It's derived from CK. It's derived from CK, but it's not so much. This isn't so much of the act. It doesn't give you back the actual norm so much as it gives the like a similarity measure between your x vector and your ck vector. So you can derive the norm from, you can sort of try deriving, you can derive the norm from that, especially if the norm of ck would be, if you know the norm of, if you like sort of know where the centroid is for ck. Yeah, I just say read it. I would honestly say read the paper.
What size of the problems can you solve with the IBM computer?
So it's 5 qubits. So any integer from 0 to 31, if you're unsigned. Really, it's meant for just manipulation of it's really meant for like manipulation of single bits. So your vector would either be, your feature vector is either going to be like 1, 0, or really, you only have two parameters available for each qubit in your feature vector. The trouble with making this is that IBM's actual quantum computing setup is built using superconducting qubits, and trying to actually implement control over that entire space of 5 qubits, and trying to implement control over all the terms that you get trying to implement control over all the terms of the Hamiltonian is actually really difficult work, especially when you're trying to build physical systems, because again, one stray photon goes to the system, and all of a sudden your quantum computer collapses. So it's a 5 qubit system. In terms of computing problems, it's really we're seeing the most basic level at this point. If you had a kilobyte, if you could build a quantum computer that had memory even like 1,000, if it had memory even a kilobyte, then you'd get, Nobel Prize in Engineering and tenure at a university of your choice. Don't think of IBM's computer so much as a quantum QPDP-11. Think of it more as a Quinac, as a really everybody says quantum computing or classical computing was in the 70s. It's more like it's in the 40s or the 50s. So really just experimenting with the technology, trying to getting these systems up and running. Yes?
My question is about optimization. So, from my understanding, quantum computers will allow for faster optimization algorithms and methods. My question is, are you aware of the current state of research in this area and quantum optimization algorithms, and perhaps how they've been applied to machine learning? Because most machine learning boils down to an optimization problem. And I'm wondering if things like quantum annealing have been thought of as a black box to plug into instead of like gradient descent or something like that.
I've certainly heard of this stuff. I haven't done too much research. I haven't done actually too much research into these systems. I assume you're talking about I'm guessing you're talking about something like what D-Wave is doing with their quantum annealing system. So yes, you can do some work with. There's definitely been work with quantum annealing. But there's also been some competing papers that have been saying like they don't have full control over it. They don't have full control over their system, so it's more of a quantum six. It's more like a quantum simulator than it is a full complete quantum computer that you can do with these problems. Nevertheless, the optimization. I think optimization-wise, I wouldn't be at all surprised if D-Wave was able to make some progress with this. Although it would be less of a full quantum computer and more of a quantum ASIC. But again, I don't know enough about their technology and enough about the industry itself in order to say how far that's going. You can definitely do stuff like this. You can definitely get some kind of quantum speed up when it comes to work like this. But as you really start to get like the hard optimization problems, as you start looking at things like NP complete problems, then really your quantum computer science. There hasn't been enough research into quantum computer science to really start attacking the P versus NP problem. Looking at just what kind of problems you can solve that are in NP that you can that you can speed up or even do it in real time if you wanted to.
So technology-wise, the solution for quantum computing will be a hybrid between a classical and a quantum, yeah?
Yes. So this won't be in terms of streaming video, in terms of everything we're doing on classical computers today, you can expect to see that. You can still expect to see that for a long time. Quantum computers are very much going to be like computers back in the 70s. There'll be some deep basement somewhere. There'll be a deep basement in a lab that some skilled people are going to do. The advantage of it, though, is that I imagine there's going to be a lot of SaaS applications, or platform as a service or PaaS applications, where you'd be doing a lot of you'd still be doing a lot of classical computation, but for hard problems or for a particular optimization problem. Like for example, this clustering algorithm. That assignment procedure is still a classical step that runs on a classical computer. The only real thing that's quantum about it is measuring that norm. But since measuring the norm is the slowest part, if you can offload that, if you can speed that up, you'd speed up the entire algorithm. You speed up the entire algorithm. So it'll be a hybrid approach. I imagine that you won't be calling your quantum program. You have specialized quantum programs that will be specialized computation problems.
How many bits do you think a quantum computer will have to achieve in order for it to be useful for applications outside of the research area that you're in?
So looking at the nice thing is you get exponential scaling between qubits and classical bits. So simulations I've seen are about 30 qubits. So about 30 qubits. I've seen simulations of that system that are currently running on major supercomputer clusters. The work I did was trying to be useful to trying to be a 96 qubit system. That unfortunately, to a 96 qubit system that cannot be simulated classically in any known algorithm. I would say that as soon as you start seeing full quantum computers that are even past the 40 qubit boundary, that are past the 30-40 qubit boundary, at that point you'll see some real applications when it comes to
Does the community have any sort of sense about what time frame that'll happen? Is there any way to do any sort of rough projections, like 30 years, 20 years, or is that pure speculation?
Any time horizon more than 3 months is pure speculation.
I know, with fusion reactors, I understand, yes. But I mean, if there's any sort of ranges of discussion in that sort of area.
I don't think we can. I haven't been able. I'm caught up on any. I haven't been really involved in any sort of rough projections. I think that's something more for the professors to decide as to when their next grant proposal, by their next research grant, they'll come.
I mean, the question is almost like, will you be a grandfather will your children have children by the time your algorithms you're working on actually will be run by actual machines?
Yeah. Well, the thing is, I can't really say. Most of the work I did at ITC was just looking at all the spin-off projects from these two systems. The system I was working on involved looking at, say, spins between it was looking at spin-labeled amino acids, and that's a 2 qubit system. And you can still glean useful data from that, like finding the distance between, if you can find the distance between 2 amino acids in a protein. It's not exactly quantum computing, but you can use this quantum circuit framework to model it. With quantum cryptography, for example, that might be one of the first commercial applications of quantum computing. Those are 2 qubit systems where you're generating entangled states, and basically when you read 1 qubit, you can infer information about another qubit. So in terms of quantum computing being actually used to solve the traveling salesman problem, or being used at Amazon to optimize in order to optimize network scheduling, that's still a little far off. I don't think we've hit the scaling at the point where we can see this. I can't say anything serious, but I think I think when we hit the point where we see the first commercial applications, it's going to scale out. It's going to scale out like crazy. We have a huge body, so there's been 20 years of research into the quantum computing field, and unlike with classical computers, now we have classical computers where we can use to model these. We can use smaller solutions. So there's a whole bunch of. So if you talk to some of the mathematicians at ITC, they have a whole bunch of killer apps that are ready to go on a quantum computer. They just need a quantum computer. So
can I ask something a little bit off the wall? Among your community, what is the attitude toward I forget the name of it, the mini world hypothesis? In terms of, I've heard this physics community, apparently a large number of them really consider that to be a real reality. Do you ever talk about that sort of thing, or is that sort of just not even that?
Philosophizing is not. I'm not really much of a philosopher. My background in engineering. Frankly, if the model works, use it. In terms of, I can't even begin to speculate. I can't even begin to talk about the many wolf hypothesis or the on that hypothesis. But that's really one thing is kind of outside the scope of this model.
Right.
But at the same time, if you look at modeling, there's some interesting results you can get if you model both an observer and an event as quantum events. You can get some interesting physics that behaves sort of like observation behavior and have some interesting propagations. As to whether it means that there's a second universe that splits off every time a wave function collapses, we really can't measure that.
It's really a matter of philosophy, I guess.
It's a matter of philosophy. It's a matter of how you see it.
Again, everyone's going to be great.
So yeah, can we? I think Mary is just saying we'll discuss it after the break.
Oh no, it's just
Okay, sure.
Okay, so I was hearing talk about 30, 40 qubit quantum computers, which is where they could actually get useful. So what's the largest quantum computer that's been built as of yet in terms of number of qubits?
In terms of number of qubits, if I remember correctly, I think that five qubit computer is huge by comparison. So 5 back in the early I don't have good figures on this, but they were able to prove some very basic stuff on in 2006. In March, they were able to implement a Fredkin gate, which I kind of showed here as that swap gate. They were able to do that in a physical system, so that's a 3 qubit computer. In terms of current qubit size, it really depends on your implementation. The number of implementations of quantum computers is bigger than the number of qubits there are, and each one has its own advantages and drawbacks. So for example, nuclear magnetic resonance, NMR quantum computers that actually use physical spins in a chemical compound. Those can be about 2-3 qubits. Really, the scaling problems just haven't been solved. They've been limited. Really, you'd struggle to see a quantum computer bigger than 5 qubits.
But you are excluding D-Wave, yeah?
I'm excluding D-Wave because it's not verified as to whether that's an actual fully real you won't have full control.
I think we're pretty confident it's not even close.
Yeah, we're pretty confident it's not even close. D-Wave. D-Wave, just you can do quantum annealing. Sure, you can do on 4,000 qubits or whatever, 4,000 of their qubits or whatever they're throwing on. But you can't stay at a very particular. What you can do really is just prepare a state, cool it down, and just say, okay, you can't really say, okay, I want to flip this spin over here. I want to write this state of this and do an entire Hadamard do a Hadamard just on that spin. You don't have nearly the level of control that would be needed in order to make a full quantum computer. So. So 5 qubits, IBM gives you 5 qubits. I found in my 3 hours of playing with this thing that's more than enough to get everybody started. And then as you go out to bigger systems, the challenges get a lot harder. Right.
Thank you.
I hope I was informative.